Welcome to the BIOCON-CO2 third webinar on engineering sustaining Bio-CCU, solubilization, reactor design, and downstreaming. The purpose of our webinar series is to increase our community outreach for the project, establishing long-term partnerships between our consortium and our future users. Each webinar is dedicated to a specific aspect of the project with a special focus on further development, upscaling, and industrial uptake. You can find our past webinars on our website, including Bio-CCU potential and opportunities, and CCU biocatalysts, how to get them out of the lab. Please note we have upcoming events. I hope you will be able to attend our Policy and Economic Perspectives webinar and our final symposium, which will take place in Ghent, Belgium on 14th and 15th of June. And for these events, all of the registered participants today will receive an email invitation, so you will have the information on joining these events. Just a word on logistics today. The webinar is recorded and will be made public via the project website. All of the attendees are muted, but you are welcome to ask questions at any time through the chat window. We'll be happy to check questions and answer them after each presentation. And then we have a panel discussion at the very end of the webinar, where we will open discussion and unmute all of the attendees. So you can raise your hand, unmute yourself, and ask any question. Our program is pretty full today. In fact, after the welcome and introduction, we will take a look at the trickle-bed reactors for CO2 fixation, and then the advances in small-scale process development for fermentative CO2 utilization, and then a decision-making tool that's been developed for downstream processing, Pervaporation and its application to the downstream of alcohols, Nanofiltration and reactive extraction and its application to the downstream of formic acid. And then, as I said, we will wrap up with a roundtable on any questions you may have. So now I will hand over to Montse Bosch, who will present the next project overview.
Okay, thank you. Welcome everyone again. Thank you for your interest in this webinar. I just give you a brief introduction of the project, just to have a quick view of what we are doing during this interesting project called BIOCON-CO2. Let's see if I can move. Sorry. Here. Yes, here the most interesting information about the project. It's a project funded by the European Commission under the Horizon 2020 program. The project starts January 2018 and will finish in June of this year in 2022. We have an overall budget of almost 7 million euro, and it's coordinated by LEITAT. You will see in another slide that we are 18 partners located at 8 different European countries. The project is, or the aim of the project is to transforming raw CO2 waste from iron and steel, cement and electric power industries into value-added chemical and plastics. Why we proposed some years ago to perform this project? Because it's a need to reduce the greenhouse gas emissions and avoid overexploitation of natural resources. How we intend to contribute to this big goal. Developing and validating a flexible platform, a flexible strategy to biologically transform CO2 into into value-added chemicals and plastics. And yeah, doing so, we will contribute to increase the sustainability of the chemical industry, also providing support to European leadership in biological CO2 reuse technologies. So, yeah, this is sorry, because there is a little delay on the here. This is more or less the scheme of the project. As I mentioned, BIOCON-CO2 is a versatile platform where we where we divide the process of conversion or bioconversion of CO2 in added value in 3 steps. The first one is focused on developing strategies to increase the solubility of CO2. So here we will see after that in one presentation, one of the technologies that we are developing during the project. In the second stage of this process, it's the microbial cell factory development itself. And the third stage of the project is the downstream technologies. You will see also several strategies that we are studying during the project in the later presentation. So we are able to, we are designing technologies and tools for these different stages. The one for CO2 solubilization, also for the bioconversion of CO2 into chemicals and plastics, and for downstream technologies. And these technologies are combined based on the properties of the microbial cell factory itself and the product that we want to achieve with this microbial cell factory. In fact, we are developing, we are demonstrating, or we are trying to demonstrate this platform in 4 different microbial cell factories with different type of microorganisms. Cell factory 1, we are working with anaerobic microorganisms in order to convert CO2 in alcohols, in branched alcohols. In microbial cell factory 2, we are working with aerobic strain, aerobic bacteria called Bemidus necator, in order to produce poly-3HP. And we have 2 other microbial cell factories focused on using enzymes. In one case, the formate dehydrogenase enzymes to produce formic acid from this CO2. And in the microbial cell factory 4, we are using a multi-enzymatic pathway just to produce lactic acid from CO2. We are also studying during the project the possible application of these compounds with these chemicals and plastics that we are producing in different industrial sectors. From one side, the branched alcohols, biopolymers, as you can see here, but also as feed additives. We are 18 partners distributed in 8 countries. The consortium includes large industries such as the ones you are seeing here: ArcelorMittal, Arkema, MG Arctic, and Measure. We have also SMEs in the project, mainly focused on PERVATECH. You will see later focused in one downstream technologies, aquaculture for the dissemination and exploitation activities, and also data and notation sciences as end users for feed additives and plastics markets. We have also several RTOs working collaborating in the project, which is with by LEITAT, but also the bio-based pilot plan in Europe, TECNALIA and Fraunhofer, and also several universities, which the University of Groningen, in NTUA in Greece, the UAB in Barcelona, also the University of Aachen and University. So the expected results that we expect to achieve at the end of the project is to assess and validate 3 different systems, processing systems, using biotech. As I mentioned, we have 3 different production systems, one based on aerobic aerobic bacteria, other anaerobic bacteria, and also enzymes. in order to convert these CO2 emissions from iron and steel industry into valuable industrial products. Also, we are aiming to produce 4 chemical building blocks using these strategies for applications in different industrial markets, as I mentioned before. We are also constructing a pilot plant that will be installed in an industrial setting, just to demonstrate and validate the effectiveness of this, at least the most promising microbial cell factories using this CO2 directly, real CO2 effluents. And also we have a lot of activities with the aim to improve the public perception of CO2 reuse technologies through this responsible communication, knowledge transfer, and exploitation project outcomes. As I said, the project today is focused in technologies. We will see, as Susan mentioned, one technology, two thoughts related with this stage 1 of CO2 solidation strategies, and also the others are focused in the downstream processes, because we had held another webinar focused on these microbial cell factories. So that's all from my side. Welcome again to this webinar, and I hope that you enjoy it a lot. So yeah, I give the, so Susan, please. Thank you. Thank you. I want to also thank you, Susan, to the organization of the webinar.
Great. Thank you very much. Let's move on with the next presentation from on the Trickle-bed reactors.
Thank you, Susan. I'm not sure if I have the control now.
Yes.
No, I can't.
Sorry, my fault. It should be okay now.
No, not yet.
I see someone moving the mouse.
Oh, yeah, it's me now. Thank you.
Okay.
Okay. Hello, everyone. Thank you for coming to this workshop about BIOCON-CO2 project. My name is Rubén, and I will present with Mari Carmen the use of trickle-bed reactors in CO2 fixation. Okay. First of all, we need to know what a trickle-bed reactor is. Well, a trickle-bed reactor is a chemical reactor in which we put into contact 2 different streams, liquid and gas, to produce a chemical reaction. Normally, the movement of those streams are in countercurrent, injecting gas from the bottom part of the reactor and the liquid from the upper part. To accelerate the reaction between these 2 streams, a bed of catalyst is placed into the reactor. The catalyst can be organic or inorganic, depending on the reaction that will take place. Hydrodynamic of these reactors are extremely complex, and nowadays the study of these reactors are still in progress. That means that it's appearing every year several publications about it. According to most of the authors, the basic configuration of trickle-bed reactors can be classified in these 3 categories on the screen. A conventional trickle-bed reactor is one in which the packing material is randomly packed, as you can see in the figure A. A semi-structured trickle-bed reactor, in this case, in this reactor, the packing catalysts are structured. That makes possible work with lower pressure drop and eliminate the limiting factor of diffusion of the reactors. And in the last point, the micro trickle-bed reactors have microchannels with the catalyst that allow to have a better control of the reactions, which make the process safer. Before to start using a trickle-bed reactor in our processes, it is important to know the advantages and disadvantages of these reactors. The main disadvantages of trickle-bed reactor is the control of the distribution of the liquid and gas within the reactors, which usually makes channeling. The fluid dynamic, as we said before, is very complex, and due to that, the scaling up is very difficult. On the other hand, we have numerous advantages, such as the large volume processing, the energy consumption, which is very low, or the high elimination capacity of the system. The trickle-bed reactor are used in a wide range of processes because of the advantages of this kind of reactors. In processes such as the oxidation of harmful chemicals, compounds present in wastewater, or in wastewater plants where the biomass resides on the packing materials. In BIOCON-CO2 project, we based on the fixation of CO2, like in the last case, trying to place biofilm on packing materials. In these projects, the use of Cupravidrus necator as microorganism for biofilm formation was used. We used different packing material to test the behavior in our environment and see if they are degraded or not over the time. And now Mari Carmen will present some of the results we obtained within the project about the packing material tests. So Mari Carmen, if you want to continue, please.
Yes. Well, as Rubén mentioned, trickle-bed reactor requires and contains packing materials inside it. They are the responsible of the adhesion and the growth of the bacteria, and the bacteria are producing in their metabolites the compound of interest of the targeted compounds. Although to promote this adhesion and growth of the bacteria, several parameters are influencing. For example, the electrostatic interaction between the support and the bacteria. As you know, exist different bacteria with different charges, and yes, and the opposite charge is promoting this adhesion between the bacteria and the support. Then the surface area and the surface roughness of the support. Exist different types of bacteria with different shapes, as spherical, rod shape, or flagellar. That this shape has to fit on the surface morphology. Then hydrophilicity or hydrophobicity. It has been reported better cell adhesion in both kinds of substrates. It depends on the nature of the bacteria. Then as well the availability of the nutrients, and finally the shear forces. There is shear forces between the packing material and the solution, and this possibly could reduce the deposition of the bacteria on the surface. When thought in trickle-bed reactors, these shear forces are small. The conventional packing material used are the rushing rings in this kind of reactors, which provides a large surface area within the reactor. Has a random packing, which is also an important parameter, but this as a disadvantages, they present a high economic cost and are petroleum-based materials. Okay. In BIOCON-CO2 project, we investigate new packing materials, efficient, environmentally friendly, and low cost. Since we all came from industrial pre-consumer waste. In this case, we select 3 different kinds of materials. First, the polyurethane foams, fibrous materials, where we have different kinds of structures, woven, non-woven, and 3D. Two kinds of hardwood chips, and finally polypropylene pellets. And here we have represented the bacterial growth on the fibrous materials as we registered these images by electronic microscopy, and we can see as all the fibers are covered by the bacteria of interest in this case. And then after characterize and work with all the packing materials, we also work in this project with plasma technology. Plasma is a partially ionized gas composed of electrons, ions, photons, atoms, and molecules with negative global electric charge. In this case, this modification of the surface could promote the biofilm formation. Since with the plasma, what we can do a surface cleaning without modification of the intrinsic properties of the material, using normally in this case plasma gases. We can use oxygen, helium, or nitrogen, for example. These gases, what they do, they modify the surface, the morphology of the surface, and are introducing non-permanent functional groups, normally polar functional groups. Meaning that this activation is lost with the time, and we are not generating bonds or in the surface. And using these gases, we can increase the roughness and the surface area of the surface. Then what we also can do with plasma is the deposition of functional groups, permanent functional groups. In this case, we need to use liquid compounds that can polymerize or can be bonded on the surface when we apply the negative charge. And all this process, when we have the liquid compound and the polymerization permanent on the surface, we are doing nano coating by what we call pressure PCVD, pressure enhanced chemical vapor deposition. And this technology presents several advantages, since we don't have water consumption or wastewater effluents, we don't have chemical consumption, and we can avoid drying or curing processes. And as well is a well-controlled and reproducible technique. Okay, here we have an example of the treatment of plasma using gases, meaning that we are modifying the morphology and introducing polar permanent groups. And here we can see a fiber without treatment and one treated, and we can see as this roughness is increased, and we optimize the conditions of the treatments, since we can play with electrode distances, gases, and power. And in this case, with this increased roughness, we observe as well bacterial growth. Sorry. Then, after the treatment using the gases, we also work with chemical deposition using plasma. In this case, before the chemical deposition, what we used to do is an activation step in order to promote the bonding of these compounds on the surface. In this case, we selected two different monomers with different nature, the acrylic acid and the hexadimethylsiloxane. And here we have as well the plasma condition. And with this, what we obtain is two different surfaces, hydrophobic and hydrophilic. And then we can observe what is better to promote the bacterial growth. And in this case, we observed as in the first case, when we had acrylic acid and hydrophilic surface, we observed the bacterial growth, and in the other case, we didn't observe bacteria on the surface. And with this, what we can say about the plasma technology is that is a versatile technology. in which we can tune the surface properties to promote or not, in this case, the bacterial growth. And then, as a conclusions of this part, in BIOCON-CO2 project has been demonstrated the viability of trickle-bed reactor used for the CO2 capture. We also studied 10 different packing materials and has been evaluated by means of surface characterization, behavior inside the reactor, and biofilm adhesion and growth. As well, it was determined the capability of the packing materials to create biofilm by cupravidose negator. And as well, we did some plasma treatments on the selected textile to see the effect of the changing properties on the surface on the bacterial growth. And we use atmospheric plasma using gases to increase the roughness of the surface. We also use PCBD plasma with liquid compounds to functionalize the surface with permanent functional groups. And we also studied the surface properties and biofilm formation. We also observed that the surface properties and biofilm formation can be tuned, changing the plasma conditions. And nowadays, it is expected to have a publication with some of the results. And thank you. This is all from our side. If you have questions.
Let me check the question panel if we have any questions so far. I don't see any, but as I said, you are free to type your questions in the chat window and we can answer as we go. Otherwise, let's continue with our next presentation. Aline, when you are ready, go ahead.
I'm ready. Thank you, Susan. And you're ready to click through the slides. So yeah, welcome to the next presentation. And I'm happy to tell you a little bit about our advances in small-scale process development for fermentative CO2 utilization. You can go, yes, thank you. If you look at the state-of-the-art for process development for gas fermentation, there are like two systems we are basically using, which on the one hand is a serum bottle in the small scale, and the next one is just the fermenter in the next bigger scale. So, and the serum bottles and fermenter have different benefits or disadvantages. So for the serum bottles, we do not have any online monitoring. And it's also, we just have a batch gas supply, which is not sufficient for really continuous fermentation with gas fermentation, but we do have a high throughput if you want to screen multiple organisms. Going into the fermenter, we do have online monitoring and we do have a continuous gas supply, but there we are highly limited in the throughput. And therefore, for early state-of-the-art process development, we were asking ourselves if there is something to fill the gap. Next slide, please. You can also, and to fill this gap, we designed the gas shaker system, which shall be in the middle between the serum bottle and the fermenter, which is a shake flask system with online monitoring, where we do have a continuous gas supply and could highly increase our throughput and our data generation for really directed process development. The next slide, please. The measurement principle in the gas shaker system. So if we're looking at aerobic cultivation, everybody knows about the oxygen transfer rate, which is basically the rate our organism is respiratory activity. So just a basic measurement for the activity of the organisms. So looking at gas fermentation, these parametrics are not existent yet, and we were thinking about another parameter just to get insight into our cultivation and how the microorganisms are behaving. So therefore, we looked at the gross gas transfer rate, which can be determined by a pressure sensor installed at the top of the shake flask, and represents the total gas transfer into and out of the liquid phase measured in the headspace of the shake flask. Next slide. And what we also developed was a carbon dioxide transfer rate calculation. So by installing a CO2 sensor also into the shake flask, we were able to measure the CO2 concentration, which can also be a parameter to get deeper insight into our process. Next slide, please. So overall, the gas shaker is a device for gas fermentation in shake flask. And with this device, we are able to simultaneously cultivate in up to 8 shake flasks with a gaseous carbon source. We are able to individually adjust the gas composition we are using, and it's also safe to use with toxic gases like carbon monoxide and hydrogen, which are the relevant gases in this project. So on the right side, you see the basic application installation of the gas shaker system. So we have a gas supply on point 2, the gas shaker system, and a computer, like a data evaluation unit. And if we look at the next slide, I will give you a deeper insight how the gas shaker system is installed. So this is a brief schematic view over one shake flask in the gas shaker. So the whole system consists of 2 valves, an inlet valve and an outlet valve at the 2 ends of this overview. And then we have a loop installed just in the headspace of the shake flask, in which a carbon dioxide sensor and an overall pressure sensor is installed, and a membrane pump which pumps the gas from the headspace of the shake flask to the individual sensors. So how is the gross gas transfer rate measured? As said before, the gross gas transfer rate is basically just the sum of the overall gases in our system, like you see here on the left. Next slide, please. More in detail, we can look at the gross gas transfer rate on the right side. Just let me explain you through this diagram. So if we do think about a system where, for example, like a relative basic gas fermentation system, carbon monoxide is the sole carbon source. Carbon monoxide is represented in the right diagram as the pink dotted line. So within the gas shaker system, we have 2 phases, a flush phase and a measurement phase. During the flush phase, indicated with the open valve, is phase 1. We have a continuous gas supply into our shake flask. During the measurement phase, indicated here as section 2, we close the valves, and during this measurement phase with our sensors, we can determine the consumption and the production of gases. So if you look at just the pink one, as carbon monoxide is the carbon source, carbon monoxide will be consumed during the measurement phase. So we do see a decrease in the carbon monoxide partial pressure. Simultaneously, looking at the stoichiometrics, by most of the organisms, while consuming carbon monoxide, they are also producing carbon dioxide, which is here shown in as the green line. So for the overall gross gas transfer rate, it will result in the black line we see here, which is just the sum of those 2 gases. And this is also the point why we installed carbon dioxide sensors in the system, since carbon dioxide is really accessible to measure and gives us a deeper insight in how this gross gas transfer rate, what this really means. So how much carbon monoxide, for example, we are consuming. But looking at our target gases, like the gases of industrial steel plants, there's not only carbon dioxide and carbon monoxide in the gases, but there's also hydrogen. If you go on the next slide, please. So by adding hydrogen to the system, we can also see different effects on the gross gas transfer rate. Just keep as a reminder, the gross gas transfer rate is just the overall pressure change in the system. So by the addition of hydrogen, the additional hydrogen consumption, displayed is the blue dotted line, can increase the carbon dioxide, can increase the gross gas transfer rate because when we have additional hydrogen which is consumed, of course the overall pressure will decrease. But also adding hydrogen to the system can enable some organisms to additionally consume CO2, that we could go from a excess CO2 production always also into an excess CO2 consumption, which is our overall goal in the BIOCON-CO2 project. So this is just an introduction to show you a little case study we performed with the gas shaker system. On the next slide. Just to see what the system can do, and one main point on in designing some the process development for fermentative gas fermentation is gas transfer rate. So is the cultivation limited by adding enough carbon or enough energy into the system? And therefore, we investigated in the gas shaker system the effect of different gas transfer rate and looked at the effect of gas consumption via the gross gas transfer rate and carbon dioxide conversion. And we looked if we can see an increased product formation in these systems. On the next slide, please. So how did we do this? The system is a shake flask system, and how by just easily increasing the shaking frequency in your shake flask, you're also increasing the maximum gas transfer rate. So, and this is what we've done, and I will show you in the next slides. So here we now see the results, or later see the results of our case study. The organism we were using is Clostridium lungdali, which is an organism which can consume syngas as a source to produce acetate and ethanol, while ethanol in the BIOCON-CO2 project, of course, is our target product. So on the left side, on the top graph, we will see the product concentration. In the middle, we see the gross gas transfer rate, and at the bottom, the CO2 TR. And I will now go with you through these results. Next slide, please. Thank you. So looking at the offline data, we measured the product concentrations. We do see that with an increasing shaking frequency from 100 to 200 to 300 RPM, the acetate production is increasing from 100 to 200 RPM, but will stop if we increase the shaking frequency further. Just as a reminder, an increased shaking frequency results in an increased gas transfer rate. Looking at the ethanol concentration, we do see that at 100 RPM, we nearly see no ethanol producing by the organisms. At 200 RPM, the ethanol production increases, and it increases further with the increased shaking frequency to 300 RPM, ending at a final maximum ethanol concentration of around 15 grams per liter. What is also interesting is that we can see a metabolic shift at 300 RPM, while the organism stops producing acetate, just goes into the production of ethanol. Looking at the gross gas transfer rate. Next slide, please. Yes, thank you. This shows the overall gas consumption in the system. Just as a reminder, negative values mean gas consumptions. As we expected, with the 100 RPM, we do see that the organism starts to consume gas until it reaches a plateau, like the plateau between 36 and 48 hours. This indicates that we do run into a gas transfer limitation, since with the 100 RPM, there's not enough gas put into the shake flask. This is also proven by increasing the gas transfer rate further to 200 RPM when we see a really steep increase in the gross gas transfer rate. But with the shift to 300 RPM, the overall gas consumption decreases until the cultivation is more or less over and around 130 hours. Another interesting point is now if we look at the carbon dioxide transfer rate, since this is our target in this project as well, what we do see here that for the shaking frequency of 100 and 200 RPM, we do see no excess carbon dioxide consumption. Why do I say excess carbon dioxide consumption? Is when we would just solely consume carbon monoxide in this system, we would see carbon dioxide production, as I explained before. But since we have additional hydrogen in the system, the carbon dioxide produced by the organism itself is already consumed with the additional hydrogen. So this is what excess carbon dioxide consumption means. But if we see the increase to 300 RPM, the organism shifts and we do see an increased carbon dioxide production. And this is not what we really want in our system, since we do not want to produce more carbon dioxide. This is most likely related to increasing gas transfer rate, which leads to hydrogenase inhibition in the organism. Since carbon monoxide is also the carbon and energy source in this point, but also has some toxic effects on the organism. And overall, this is really interesting and gives us a deeper insight into the behavior of gas fermentating organism, and we can use this data for going into scale up and setting the process parameters for fermentations, etc. If you go to the next slide, please. So overall, the gas shaker system is a novel shake-fast system for online monitoring of gas transfer rate, and is applicable for process development. And it enables us to analyze gas transfer rate and the measurement of the gross gas transfer rate, the carbon dioxide transfer rate, and enables deeper insights into the small-scale gas fermentation processes. And therefore, I thank you for your attention, and I'm ready for questions if you have any, or of course later in the round table.
Thank you very much, Aline. All right, moving on to our next presentation about the decision-making tool. Carlos, you should have control over the slides now.
Let me check. Yeah, it looks like it. All right, yeah. Okay, so the mouse is moving, but I cannot finish the slide. Let me check with mouse.
You may have to click the arrow at the bottom of the screen.
Okay. Okay. So hello everybody. I'll be talking about a tool we have developed for the downstream process related with the BIOCON-CO2 project. So first of all, I'll talk about what we were aiming for, and then I'll be talking about the steps the user needs to take to use the tool with a glimpse of theory. So when we decided to develop this tool, we wanted to develop a tool for the whole consortium. And of course, there are already software out there that is available, but we wanted to avoid problems related with software licenses. If you go for a commercial option, then you have to buy a license, and then you cannot share it with the other partners. So we decided to go our own way. And also at the same time, these kind of softwares, they are kind of complex. They allow you to do lots of stuff. But for our purpose, we did not need so much capabilities. So we wanted to be a tool that was straightforward and user-friendly. So that we implemented the DOE, so the design of experiment, limited to 2 to 4 variables, which is usually what you find in the lab. And then we base that in the response surface methodology, and then with some common regression analysis and linear least square method, where basically what we have done is you take a typical formula A, x squared plus bx plus c, and we added, well, you should add some interaction variable that allows you to work with more than one variable at the same time. And at the end, we apply some implementation, and we focus all of that to the optimization of the downstream strategies for the compounds we are aiming for in this project, basically lactic acid, polyhydroxybutyrate, and C6 alcohols. Although it is not limited to that kind of components, it is just the component we remember. At the end of the day, it is just a mathematical tool, so it doesn't see components. It's just X, Y, and Z. So first of all, what is DOE? Let me read it. The basic definition of a DOE is the design of any task that aims to describe and explain the variation of information under conditions that are hypothesized to replicate variation, which means that we want to know how our independent variables affect our dependent variable. Of course, we wanted, well, you want to have some prediction capabilities, and what DOE allows you is to have these prediction capabilities along with studying multiple variables at the same time, including interactions, as I mentioned before. But it is important to keep your foot into the ground and constrain your system into the reality. Because at the end of the day, you have to perform the experiments so that you cannot, for example, you cannot put a set of data too close together, because you will enter into the realm of the experimental error. So usually when you working in the lab and you want to test how a parameter will affect your desired variable, you fix one. For example, in here you have pH versus volume. You will usually start at a point, a fixed volume, and then you will start varying the pH and see how the system responds. And then you will go back to the initial conditions and check the volume independently. However, doing that way, we will end up working. I'm not sure if you can see my mouse, but I've got a nice blue arrow there. We'll end up working in that region where you're actually missing the sweet spot for your process. So what we do with the design of experiments is we build up around a point or a set of conditions we establish. You build that around it a square in case of two variables, a cube in case of three variables, or a different figure in case of 4 or more factors, so that we spread our points and we can analyze all of them more or less at the same time. Okay, so in our tool, I'm not sure if you're able to see it, and my screen is quite small. First of all, we will choose the number of factors or variables we want to include into the system. Then for smaller, for 2 or 3 variables, we will suggest to use the direct design. You have always the option to go for a free design where you can change the variables as you want, because the tool allows for the user to see the code behind it. But for most applications, we will just go for the directed design, where we chose the circumscribed central component design. I'll talk a bit about it later. And then we'll need to set the boundaries. Of course, if you are working with pH, for example, you cannot set the boundaries beyond 14 or below 0. So you have to always keep in mind that you, although mathematically you're trying to describe a real system. And about the circumscribed central composite, what it does is, out of the square I showed you before, it takes some values out of that square so that we get a bit of information outside the boundaries we have set, so that the software can see how the response will react outside that boundary and describe better what is happening inside of the boundary. So at the end of the day, the DOE is more or less, we prepare our system, we organize the input to get the best response out of it. Then, once we have introduced the data into the software, we will go for the RSM, so the response surface methodology. What we get out of the software is a 3D mesh or surface, and this response surface methodology evaluates the effect of those factors into your variable. Okay, so since you are able to check several variables at the same time, you kind of see physically, so in 3D, as you can see here at the bottom, you can see what the response will look like at different conditions. What happens? The more factors you add, the more complex it becomes. So this methodology usually it is kind of limited. In case we will have just 2 variables, we'll get just one of these graphs. When we go for 3 variables, you get 3. And if you go, for example, for a 4th factor, you will multiply this by 2 and you will get 6 different responses that you have to analyze independently to look for the optimal conditions. So in RSM being explained, after we have introduced our set of conditions into the software, it will suggest us, as you can see here, it will suggest us some conditions for our experiments. We will perform these experiments and we will give the software the outcomes we get out of those experiments. And with those outcomes, we can go for the to print this surface. Since we are getting, well, for this example, it is a 3 variable analysis. We've got 3 different graphs, and we need to fix one of the parameters to see how the other 2 affect each other. Of course, something really nice is sometimes you do this analysis and you see that my ideal response is out of the boundaries I have set. In that case, there is an option to set the conditions you want to check, even though they are outside of the data set you have established. However, you have to take into consideration that the farther away you are from the dataset, the deviation or the error might be great. So after the RSM has been done, software allows you to look for optimal values. Basically, in RSM, what happens is you're looking for either a maximum or a minimum. It depends on the kind of dependent variable you are working with. Or if you're looking for something like a yield, then you look for the highest yield, so a maximum. If you are looking for energy consumption, then you will go to a minimum. And what is nice is, in case the software does not find a maximum nor a minimum, it will guide you to look for the best conditions. Imagine your surface response does not have any maximum, it's just a flat plane. Then it will tell you, okay, to find the best plane, you have to go in this direction, follow this trend, like lowering the pH or increasing the time, so that you know that your optimum might be out of the data set you have established, but at least you know the section. I'm sorry, someone has the mic on, and I hear myself. You can know the region where your ideal set of points will be. Okay, and last but not least, if you create a software, you need to validate it. You need to check that the tool actually works, especially because we have added some simplifications to the mathematical model. The number of variables that the software uses, so the original equation generates, is exponential. So the more variables you add, the number of experiments that you need to perform grows exponentially. However, the equation has some values that are repeated, like, for example, the interaction or the effect of A on B tends to be, the interaction AB, it is the same as the interaction BA. So we added some trimming of the data so that we don't need to do so many experiments. Or, for example, something like that. The interactions of three components also were removed, because usually the interactions one-on-one tend to be more important than 1 and 2 and 3 on the same parameter. And at the end, the software is sensitive on the KPIs that the user introduces. So if you introduce an KPI that is not sensitive to the variable you are introducing, then you won't get a nice result. And what we did at the end of the process is we took commercial software. Here on this image on the right is the design expert, Windows version 12. And on the left, you can see what the surface response looks like with our tool. The scale is not exactly the same, so you may see that some of them are a bit larger than the others, but at the end, the numbers are exactly the same. So we were quite happy to prove that we have come up with a tool that it works for these kind of systems. So, as a summary, we have created a user-friendly tool that allows to go between 2 and 4 variables, which usually are the most common experiments you will find. It is an open source software. Although it is not yet available in Zenodo, we had some problems uploading it. It will be available in Zenodo for everyone to have a look at it. We have included a tutorial, and at the end, we are quite proud to say that we have produced a tool that is actually being validated with commercial software. And that's all from my part. If you have any questions, please go ahead. Otherwise, Susan, you can take back the control.
Thank you very much, Carlos.
Welcome.
Let me look and see if we have any questions. I don't see any questions so far. So let's continue. And our next presentation is from Ilse. So I've given you the control over the mouse. When you're ready, go ahead.
Okay, hello. So today I will be giving an introduction to pervaporation and how it can be used for the downstream of alcohols. So pervaporation is a membrane separation technology, and it can be used to separate liquid mixtures using a dense membrane. So as the word pervaporation implies, it consists of permeation and evaporation, and it can be brought down to 3 general steps. First, the material will have to adsorb onto the membrane surface. In the second step, it will permeate the membrane from the feed side to the permeate. And in the third step, it will desorb and evaporate into the vapor phase by using a vacuum or a sweeping gas. So in general, there are 2 types of pervaporation depending on the membrane surface. If the membrane surface is hydrophilic, then water will selectively permeate the membrane. Some examples of these types of membranes are organosilica networks like the HIPSI membrane, zeolites, and polymeric membranes like PVA. This type of evaporation is often used for solvent dehydration. It can be used in combination with distillation for breaking azeotropes, and it can also be used to remove water in situ for example, esterification reactions. If the membrane surface is hydrophobic, then organic materials will selectively permeate, which is also often referred to as organophilic. For this type of pervaporation, most membranes are polymeric, and the three most common ones are PDMS, PEBA, and POMS. This type of pervaporation is used for the recovery of products from fermentation broths, and it can also be used for in situ removal, for example, the removal of products which may be toxic to the fermentation process. For pervaporation to work, there are two phenomena which are needed. The first one is that the mixture will have to be separated, and the next is that the separated material will have to be permeated through the membrane using a driving force. So for the separation, it is based on the preferential solution and diffusion interaction of one material over the other in a mixture. The first key requirement for this is that the permeating material should have an affinity towards the membrane surface. So in hydrophilic pervaporation, this separation is often based on the difference in diffusion, because, for example, water has a higher diffusivity as compared to organic materials. If the hydrophilic membrane also has a rigid pore structure, there is an additional phenomena which is called molecular sieving. For example, the organosilica Hipsy membrane has an average pore size of around 4.5 angstrom, and water with a smaller kinetic diameter than this pore size will be able to permeate the membrane, and 2-propanol having a slightly larger kinetic diameter will not be able to permeate, and this further increases the diffusion selectivity. So as just mentioned, organic materials often have a lower diffusivity, and that is the reason that organophilic membranes cannot use this diffusion selectivity, and the separation is based on a difference in solubility of the one material into the membrane material. So if you look at the water contact angle of the PDMS membrane, it is higher as compared to the one of the PEBA membrane, and this indicates that the material is more hydrophobic. And due to this increased hydrophobicity, it is able to more selectively separate ethanol, as can be seen by these higher separation factors. Then if you look at the two solvent systems, you can see that for both PDMS and the PEBA membrane, the separation factor is higher for the butanol separation as compared to that of the ethanol separation. And this is because butanol is a more hydrophobic material. So as mentioned, we not only need separation, we also need a driving force to permeate the material through the membrane. And in pervaporation, the driving force is a partial pressure gradient across the membrane. Or in other words, for that to be a driving force, the partial pressure of one component at the feed side has to be higher than the partial pressure of the same component at the permeate side. The driving force can be increased by either increasing the partial pressure at the feed side or decreasing the one at the permeate side. This first one can be increased by increasing the feed temperature, and the second one can be decreased by using a deeper vacuum pressure. So pervaporation is often considered as an alternative to distillation, and it is due to two reasons. The first one is a decrease in energy consumption, and the second one is because the pervaporation process is not affected by azeotropic mixtures, and these can be broken without the use of an entrainer. The reason for this is that in pervaporation, the driving force is a difference between the partial pressure across the membrane of one component, as compared in distillation, it is based on the difference of volatility between the multiple components. If pervaporation is used as an in situ removal method, it can also help to increase yield, productivity, and use of reactants. There are also some disadvantages to pervaporation. For hydrophilic pervaporation, this is mostly the relatively high cost to produce these membranes. And for organophilic membranes, even though these are relatively cheaper, as these are polymeric, they have a lower thermal stability, for which these are limited in feed temperature, resulting in a lower flux, and thus more membrane area would be required. So in the BIOCON-CO2 project, pervaporation was used for the recovery of the C3 to C6 alcohols from the effluent of the Clostridium lungali bacterium. And for this, organophilic pervaporation was used in combination with a PDMS membrane. So over here you can see the schematic overview of the test equipment that was used. In the vessel, the effluent is added and heated to the correct temperature. This is then pumped over the membrane surface, and the material that does not permeate the membrane is recirculated back into the vessel. Using a vacuum pump, a vacuum is applied over the permeate side of the membrane, and the permeated products will be evaporated into the vapor phase and then condensated again using a cold vac. So in organophilic pervaporation, the performance is measured in two terms. The first one is the recovery efficiency, and this describes the percentage of material that is removed from the feed into the permeate. And the other one is the flux, which describes how much material has permeated the membrane per membrane area and per unit of time. This term is often obtained using experimental work and can then be used to calculate how much membrane area would be required for industrial scale. The first step for the pervaporation part in the BIOCON-CO2 project was to optimize the pervaporation parameters. In this top graph here, you can see the effect of the feed temperature on the recovery efficiency of the products on the left y-axis and on the product flux on the right y-axis. And as you can see from this figure, with an increase in feed temperature from 38 to 70, both product flux increases as well as the recovery efficiency of the products. And the reason for that is using a higher feed temperature, the partial pressure at the feed side of the product increases, and in turn this leads to higher driving force. The vacuum pressure was also optimized. Again, on the left axis is the recovery efficiency of the products, and on the right one is the product flux. So from this figure, it can be seen that decreasing the vacuum pressure from 60 millibars to 20 millibars, both recovery efficiency and the product flux is increased. Again, a similar explanation can be used. As the vacuum pressure is decreased, the partial pressure of the products at the permeate side is decreased and leading to a higher driving force. After the evaporation parameters were optimized, the second goal was to obtain a butanol concentration of above 400 millimolars. In the first extraction, the effluent from the Clostridium lungale bacterium was added as the feed, and the butanol was concentrated into the permeate. However, the concentration was still not close to the set goal. So this first permeate was then used as the feed in the second extraction, and this process was continued until in the third extraction, the permeate had a concentration higher than the set goal. In this process, the overall percentage of butanol that was recovered was over 90%. So to summarize, pervaporation is used for the separation of liquid mixtures. Using hydrophilic pervaporation, water will selectively permeate the membrane, and in organophilic pervaporation, it is the organic material permeating the membrane. The separation in pervaporation is based on preferential solution and diffusion, and the driving force is a partial pressure difference across the membrane. Within the BIOCON-CO2 project, organophilic pervaporation was used to recover C3 to C6 alcohols from the Clostridium lungale bacterium. So, thank you.
Thank you so much, Ilse. Okay, and we can continue with our last presentation for today. Tomás, I have given you the control over the presentation.
Okay, thank you, Susan. Okay, my name is Tomás Roncal from TECNALIA, and I will talk about the nanofiltration and reactive extraction and its application to the downstream of formic acid. Bio-based products must be efficiently recovered and purified from the media where they are produced to be used in the final applications. This process, known as downstream processing, is often a complex task, accounting for a significant share of the process cost, up to 75%, mainly due to the relatively low concentrations of the target product molecules and the matrix complexity. This is also of special relevance for CO2 gas-derived products that usually are present at 1 to 2 orders of magnitude lower than, for example, their sugar-derived counterparts. Therefore, the development of efficient and cost-effective downstream processes is a mandatory need for industrial feasibility, and accordingly, efficient and non-energy intensive downstream technologies are preferred. Sorry. I will talk about 2 non-downstream technologies, first explaining their basis and then applying them in a particular case study. The first one is nanofiltration. Nanofiltration is a pressure-driven membrane-based separation technique where the pore sizes of membranes are between those of reverse osmosis and ultrafiltration. It is suitable for the separation of inorganic salts and small organic molecules. Nanofiltration is considered as an energy efficient and environment-friendly technology. Nanofiltration membranes are characterized by 2 kinds of parameters: structural, the pore size, and electrical, the membrane charge. Their pore size is in the order of nanometers, and their nominal molecular weight cutoff is in the range of 100 to 1,000 Daltons. The separation mechanisms of nanofiltration involve both steric, sieving, and electrical Donan effects. The solute movement through the nanofiltration membranes is governed by both transport and exclusion mechanisms. Transport mechanisms within the membrane include diffusion, convection, and electromigration. And exclusion mechanisms include steric exclusion, Donan effect, and dielectric exclusion. The second technology to be present is reactive liquid-liquid extraction. There are 2 types of liquid-liquid extraction, physical and reactive. Physical extraction involves the extraction of a solute into an inert non-reacting solvent, and it is only based on the different physical properties of solute and solvents, such as polarity, for example. Reactive extraction, in turn, involves a reversible reaction between the extractant in the organic phase and the solute in the aqueous phase, and the complexes formed are then extracted and solubilized in the organic phase. Reactive extraction is also considered as a clean process, since the energy demand is low and the extractant can be completely recovered and reused. Reactive liquid-liquid extraction is very suitable for carboxylic acid recovery, where aliphatic tertiary amines and alkyl phosphates are efficient extractants. Extractants are usually mixed with organic solvents called diluents, which control the physical properties of the organic phase, such as density, viscosity, and surface tension, and affect the stability of the complexes and the level of extraction. The undissociated form on carboxylic acid is the only one that can be extracted. So the pH of the aqueous phase should be kept at a value lower than the pKa of the acid. There are two steps in reactive extraction. The first is the extraction of the solute to obtain a solute extractant complex in the organic phase and a relatively solute-free aqueous phase. The second is the back extraction or the reextraction and the complexed solute from the organic phase to recover to recover the extractant-free solute in a new aqueous phase, and simultaneously to regenerate the extractant for reuse. Sorry. Once we've explained the basis of both technologies, I will talk about their application in a particular case study: the downstream processing of mixtures of formic and gluconic acids. In the framework of the Horizon 2020 BIOCON-CO2 project, TECNALIA is in charge of the downstream processing of one of the target products to be obtained from CO2, the formic acid. The process for formic acid production from CO2 is a two-enzyme coupled biocatalytic reaction involving the enzymes formic dehydrogenase to catalyze the reduction of CO2 to formic acid and glucose dehydrogenase to regenerate NADH by oxidation of glucose to gluconic acid. So, the formic acid effluents obtained are characterized by the presence of equimolar concentrations of formic and gluconic acids. According to the effluent composition, it was proposed a downstream strategy using two successive separation technologies, nanofiltration and reactive liquid extraction. The objective of the first step was to separate formic acid from gluconic acid by nanofiltration, taking into account the quite different molecular weights of both acids. After this nanofiltration step, the idea was to concentrate the formic acid from that gluconic acid depleted solution by a reactive liquid extraction process, using a tertiary amine as extractant and an immiscible organic solvent. The whole process for the separation of both acids by nanofiltration can be seen in the slide. It can be separated in two divergent lines, one leading to an essentially pure formic acid fraction, the permeate 2, and the other leading to an almost pure gluconic acid fraction, the retentate 3. The first one involves the successive nanofiltration of the feed, nanofiltration 1, and the permeate 1, nanofiltration 2, to obtain permeate 2, and accordingly can be named permeate pathway. The second one, in turn, involves the successive nanofiltration again of the feed, nanofiltration 1, and the retentate 1, nanofiltration 3, to obtain retentate 3, and accordingly can be named retentate pathway. In the permeate pathway, a formic acid pure permeate 2 was finally obtained with a purity higher than 99.6%, while in the retentate pathway, a gluconic acid pure retentate 3 was achieved with a purity of 99.4%. These two final fractions follow then two different ways. On the one hand, retentate 3 was not treated further and was considered as a gluconic acid pure concentrated solution. On the other hand, permeate 2 in turn, although was essentially a formic acid pure solution, was rather diluted and had to be concentrated. So permeate 2 followed a second step of reactive liquid extraction to concentrate the formic acid contained therein. Okay. Extractions of formic acid were carried out using 3N-octylamine, TOA, as extractant in N-octanol as diluent, and a final re-extraction with sodium hydroxide was carried out. In the final optimized process, you can see it in the table, both the extraction and the re-extraction processes were performed in 2 times, under the conditions shown in the table. A final solution was then obtained with a formic acid concentration of 174.5 grams per liter, which is 78 times more concentrated than the original feed. The total recovery yield for formic acid in the reactive extraction step was 78%, although probably it could reach 90% taking into account several adjustments related to the water co-extraction observed. Finally, the extract and diluent mixture of TOA on N-octanol was found to maintain its functionality when recovered after use, so allowing to be successfully reused in additional reactive liquid extraction cycles, as you can see in the table below. The performance is the same with a fresh mixture of TOA and octanol and with a reused mixture. And that's all for my part. Thank you very much for your attention. And if there is any question.
Thank you very much to Tomás. That was our last presentation. We have a few minutes for any questions. I do see one question about the shake flask experiments. So it says, are the shake flask experiments continuous systems? Has it reached steady state at 168 hours?
Hello, yes, thank you for the question. So this kind of like definition, if it's a continuous system and non-continuous, is quite difficult for the gas fermentation. So yes, the gas phase is a continuous system, but of course it's a batch-wise medium prepared. So it's kind of like in fermentation mode, you would say it's a batch fermentation, but we have continuous gassing. And in this case, it reached the growth is already limited, so there are just growth effects in the first 24 to 48 hours, and therefore we have kind of like a semi-steady state. Maybe this answers the question. Please feel free to type in more if I need to go more in detail.
Thank you very much, Aline. Oh, I see more questions that I didn't see before, excuse me. So we've answered the first one. I see ones that, so ethanol is stripped out via gas phase. Aline is muted.
Yes, a little bit. So, but the gassing rate in this system at the moment is 5 milliliter per minute for each flask. So we performed tests to measure the ethanol stripping, and so the results that you see are normalized. So onto the amount of ethanol we would be losing via the gas phase, dependent on the ethanol concentration, of course.
Thank you, Aline. I see another question for Tomás Roncal. Did you make an economic assessment of the separation of the acids?
Thank you for the question. No, we did not make this evaluation, because the purpose of this task in the project was simply to test the feasibility, the technical feasibility of the process. It is we have proven this feasibility, but this economic evaluation was not made. It is for further work.
Okay, and I see a last question. Which type of CO2 sensor were used?
So this is an infrared NER-based sensor made by Dynamond, I guess. So they're quite small, and yeah, based on an infrared spectroscopy measurement inside the sensor. For further, if you want a link, please email me. I'm happy to inform you with some more information about the sensors. So Dynamond it is.
Thank you. I see another question. Are CSTRs the next step, and when?
Yes, continuous are the next step. So just going not into the fermenter, we're currently at our chair. This is not my specific topic, but we're currently working at our chair the cost BIOS. If you would like to Google that. So for anaerobic system, this is already working. For aerobic, this is already a working system where we have a parallel CSTR on a shake plate base to increase the throughput. And for just gas fermentation, if you mean like this whole process, if CSTR is the next step, yes, it is. And it's performed from our partners at BBPP, and they are currently performing a CSTR with cell recycle just for the Clostridium lungdali.
Next question, what is the yield of ethanol production? How much CO2 was fixed into ethanol in the trickle-bed tests? And how much biomass is produced as biofilm? Okay, this question is about the trickle-bed tests.
Yes,
Yeah.
I think that this is the topic of Mari Carmen.
Sorry, can you repeat the question, please? Can you listen to me?
Yes, I can hear you.
Can you repeat the question, please?
Yes, of course. Which is the yield of ethanol production? How much CO2 was fixed into ethanol in the trickle-bed tests? And how much biomass is produced as biofilm?
Well, I think that question is not regarding our part.
No, I think that there's a misunderstanding here. The microbial factory that was tested in the trickle-bed reactor was Coprevirus necator, which is producing PHB as a polymer, as intracellular polymer. So the ethanol is produced by Clostridia lungdali bacteria, which is produced using a liquid fermentation process. So I don't know if you, Aline, have this data, because this work was performed by Wageningen University. Sorry, yeah, but by Fraunhofer, sorry, and they are not taking part of this webinar. It was the objective of the microbial factory itself was described in a previous webinar. So we don't have the final numbers of this conversion, but we can ask to these colleagues in Fraunhofer, and then if you give us your contact details, we can answer you later on, because it's not part of this webinar. The yields of CO2. Of CO2, the yields of ethanol from CO2 using using Clostridium lungdali.
Yeah.
So what we sorry, Carmen.
I have another question actually that's come up on the screen, a question for Aline. With the gas shaker experiments, if you do not use CO2 in the gas feed, do you see CO2 consumption? And do you need high pressure for the CO2 use?
No, so this is a good question, thank you. Maybe Susan, you can go on my last slide where just blended in like all the results. I think it must be 32 or 33, something like that. So for the question so if we just for like the Clostridium lungdali, no, the further slide. For the Clostridium lungdali, if we just feed carbon monoxide into the system, having carbon monoxide just as the sole carbon source, we do see actual CO2 production. So the organism is not consuming CO2, but is producing CO2. The metabolism within carbon Clostridium lungdali is quite complex. I'm sorry. So Clostridium lungdali is converting carbon monoxide into CO2 internally, and then so sorry, then using some of it and exhausting another part of the carbon dioxide. So high pressure can be effective, but is not yet in the term of the biomass we have in this system. So at this point, we are not limited by carbon dioxide. Since carbon dioxide is really, really soluble, we would rather have a hydrogen limitation, but further test also has shown that while you have carbon monoxide in your system, since it's energetically preferable for the organism will always go first on the carbon monoxide. And then with the additional hydrogen, it will first consume the own CO2 which it produces. And just if we keep the carbon monoxide concentration quite low, feed extra carbon dioxide and extra hydrogen, then we do see excess carbon dioxide consumption. So we performed more tests like the one I've showed you, and having actually a lower hydrogen concentration in the in-gas, so not going so high with the real amount of hydrogen, was enhancing for the organism to be able to increase the carbon dioxide use over the carbon dioxide which is produced by the organism itself. I hope.
Okay, thank you. I see one last question for Ilse. The question for Ilse is, in the pervaporation system, do you think that using thermophilic organisms would help to apply this system in situ?
Could you please repeat the question?
Yes. For the pervaporation system, do you think that using thermophilic organisms would help to apply the system in situ?
So I'm not really an expert on the bacterial side, so I'm not really too sure about what is the thermophilic part.
Okay, thank you. I think we are out of questions and also basically out of time. So let's wrap up for today. I want to thank all of our panelists from the project, from LEITAT, from RWTH Aachen University, from PERVATECH, and from TECNALIA. I want to thank all of our guests for today for your interesting questions and your attention. And we hope to see you at our next event. As I said at the beginning, the project will hold its final symposium on 14-15 June in Ghent, but this will also be a hybrid event. So we will notify you by email of our upcoming activity, and we hope to see you again. Thank you all.